So if I told you that a slight shift in wind patterns over the Pacific Ocean is about to, like, permanently erase nearly 3 years from your life expectancy, you would probably think I was pitching a dystopian science fiction novel.
Right, yeah, it sounds completely made up.
It really does. But it is late April 2026, and the ocean's latest diagnostic data is in, and the climatologists staring at these charts aren't writing fiction at all. They are bracing for impact.
It is a really sobering reality check. I mean, we look at the aggregation of reports coming out of the National Oceanic and Atmospheric Administration, the World Meteorological Organization, and specialized climate impact groups just this month. The consensus is undeniable. The
Yeah.
Pacific is flashing red. We are looking at a diagnostic landscape that is signaling a massive and potentially unprecedented shift in the global climate system.
We have a highly urgent and, frankly, pretty dense stack of source material to get through today.
We really do.
We are looking at those immediate climate diagnostic reports from April 2026. We are analyzing a groundbreaking study published in Nature Climate Change out of the City University of Hong Kong that actually quantifies the mortality of these events.
Right.
Plus, we have agricultural outlooks from Asia detailing an impending supply chain collapse. And we are examining a brand new paper from our CIV that details a dual architecture deep learning AI model built to predict these exact anomalies.
It is a formidable stack of research, and the through line connecting all of this data is the formation of what many are calling a Super El Niño.
Right, a Super El Niño.
But to truly grasp the severity of the threat, we have to move past the superficial headlines. We need to dissect the actual physical mechanics of what is happening in the water, the distinct structural variations of these events, and, the cascading failures they trigger in human infrastructure.
Because if you follow climate science, you already know the basic mechanics of an El Nino. I mean, you know about the trade winds weakening, the warm water surging eastward, the thermocline getting depressed.
Exactly. The basics are pretty well understood.
But the data coming out right now, today, is showing something way beyond a standard seasonal oscillation. Let's dig right into the NOAA and Climate Impact Company metrics.
Let's do it.
They monitor the Niño Sea surface temperature anomaly regions, the SSTA regions, and they're showing an immense buildup of upper ocean heat in the subsurface equatorial East Pacific. And this buildup is rivaled only by the infamous data from April of 1997.
And 1997 is the benchmark that makes every meteorologist sit up straight.
Oh, absolutely.
The conditions in the spring of 1997 preceded the second strongest El Niño on historical record. What is critical to understand here is the threshold.
Right.
A standard El Niño is declared when sea surface temperatures in the central and eastern equatorial Pacific rise 0.5 degrees Celsius above the long-term seasonal average.
Which, I mean, that is already a massive amount of thermal energy spread across the Pacific Basin.
Yeah.
But the anomaly we are tracking now just completely obliterates that baseline.
It does.
According to the data aggregated from Insight's IAS in the Sunday Guardian, a Super El Niño is categorized by a temperature anomaly spiking to at least 2.0 degrees Celsius. Or, in some extreme models, 2.5 degrees above average.
Yeah, we are talking about 4 to 5 times the thermal energy threshold of a standard event.
Wow.
When you reach a 2.5 degree anomaly, the standard linear models of atmospheric behavior they begin to break down entirely. You are fundamentally rewiring the global atmospheric circulation.
Now, how does that actually look in the water?
Well, the current data shows an intensification of westerly wind bursts. These are actively pushing immense planetary-scale Kelvin waves of warm water eastward.
Okay.
And this violently depresses the thermocline, the boundary between the warm surface water and the cold deep water, and it traps a catastrophic amount of heat at the surface.
It's basically like, think of the Pacific Ocean as a giant half-filled bathtub.
That is a good way to picture it.
Right. And the normal trade winds are like a really powerful fan blowing all the hot surface water to one end of the tub. If you suddenly unplug that fan, all that warm water comes sloshing violently back to the other side.
Yes, that is exactly it. And the current 2026 data shows exactly this slosh happening right now in the form of that immense upper ocean heat and those intensifying Kelvin waves we just mentioned.
I noticed a really fascinating tension in the source material regarding that exact terminology, though.
Oh, about the term Super El Niño.
Yeah. We have all these media outlets and specialized meteorological groups throwing around the term Super El Niño to describe this 2.5 degree monster. But the World Meteorological Organization, the WMO, they released an update on April 24th, explicitly stating they refuse to use the term.
Right. They were very firm on that.
They say it isn't part of their standardized operational classifications. It feels like the scientific community is having this sort of semantic civil war while the ocean is literally boiling.
It really highlights a very real struggle within the scientific community regarding taxonomy versus public communication. The WMO operates strictly on standardized historical indices.
They have their rule books.
Exactly. To their operational divisions, an event is categorized by strict numerical bands. So perhaps they will label it a very strong El Niño. Introducing a prefix like super implies a distinct, novel scientific category that hasn't been formally codified in those rulebooks.
But for governments attempting to allocate emergency funding or, reinsurance markets trying to model risk, a 2.5-degree anomaly isn't just a very strong version of a normal storm. It represents a completely disproportionate nonlinear threat.
Right, the damage does not scale smoothly.
Exactly. The infrastructure damage doesn't scale smoothly. It snaps.
Precisely. And the term Super El Niño effectively communicates that nonlinear threat to the public and to policymakers. The WMO's reluctance is rooted in scientific rigor, sure, but it exposes how our historical baselines and classifications are struggling to keep pace with the rapidly shifting extremes of the current climate.
We're basically trying to measure a fundamentally altered ocean using 20th century rulers.
That is exactly what we are doing.
So let's follow that thermal energy.
Yeah.
If we have a record-breaking volume of hot water surging across the Pacific toward the Americas, the traditional assumption, the one embedded in public consciousness, is that the west coast of the United States is about to get slammed.
Yes, that is the common expectation.
Right. Everyone expects a repeat of the 1997 event where California saw apocalyptic rainfall, mudslides, and catastrophic flooding. But the research explicitly warns us against that assumption.
And this is where the diagnostic picture becomes incredibly complex. The expectation that massive oceanic heat automatically equals massive West Coast rainfall is fundamentally flawed.
Because not all El Niños are the same.
Exactly. It ignores the structural variations of these events. We have to look closely at the study published in Geophysical Research Letters by Peck, Yu, and Kinnan.
Okay, let's break that down.
They conducted a comparative analysis of the 1997-1998 extreme event and the 2015-2016 extreme event. Both reached comparable peak sea surface temperature anomalies around 3.5 degrees Celsius in their respective peak regions.
So roughly the same amount of heat.
Yes, but their impacts on the atmospheric column were radically different.
Because the study categorizes 1997-98 as a pure Eastern Pacific, or EP, El Niño. That means the thermal mass pooled up directly against the coast of South America and the eastern seaboard.
Right. It was driven deep by the oceanic thermocline variations propagating across the entire basin. It is a deep ocean-driven machine.
But the 2015-2016 event was entirely different structurally.
Entirely different. The researchers identify it as a mixed event, heavily influenced by Central Pacific, or CP, El Niño dynamics.
And what does that mean geographically?
In a CP event, the maximum sea surface temperature anomalies never actually reach the South American coast. They stall out, they park themselves right around the international date line, essentially in the dead center of the Pacific Basin.
I want to break down exactly why it stalls, because the study introduces a mechanism that completely flips how we normally think about El Niño.
It really does.
We usually think of it originating from the ocean deep, but the study states a CP El Niño is heavily reliant on subtropical atmospheric forcing.
Yes.
It points specifically to the North Pacific Oscillation, the MPO, and the Pacific Meridional Mode, the PMM. So how do pressure systems all the way up in the northern latitudes essentially dictate where the hot water parks at the equator?
That is the crucial distinction. The Pacific Meridional Mode, the PMM, acts as a thermodynamic bridge between the extratropics and the equator.
A bridge.
When you have anomalous atmospheric pressure systems in the North Pacific, like a strong North Pacific oscillation, it alters the surface trade winds in the subtropics.
Which changes the evaporation.
Exactly. These altered winds change the evaporation rates at the ocean surface, which in turn changes the sea surface temperatures. This creates a chain reaction, a coupling of wind and temperature, that propagates southwestward down into the deep tropics. Oh, wow. So instead of the deep ocean thermocline pushing heat eastward, you have anomalous atmospheric winds pushing surface heat toward the equator, causing it to pool and stall in the central basin.
That is the exact mechanism.
Yeah.
The CP El Niño is largely driven by interactions between the ocean surface and the atmosphere, rather than the deep, systemic, basin-wide thermocline movements of an EP El Niño.
I mean, I guess it's kind of like the difference between turning on your home's main central furnace, that would be the EPL Nino, driven by the deep ocean thermocline,
I like that analogy.
versus, someone plugging in a massive space heater right in the middle of the living room using an extension cord from outside. That's the CPL Nino, driven by the subtropical atmospheric forcing.
That perfectly illustrates the difference in where the heat is coming from and where it is concentrated.
And the geographic placement of that heat pool changes everything for you, the listener, especially if you live on the West Coast.
It changes the entire outcome. Because the heat from the ocean acts like a massive thermal engine, boiling the atmosphere above it and exciting these massive atmospheric wave trains. The study maps this out beautifully.
It does.
The Eastern Pacific event, parked right off the coast, excites the tropical northern hemisphere, or TNH, pattern.
Right, and the TNH is essentially a ripple in the atmosphere that historical data links directly to extremely cold, wet conditions in the western United States.
Because the heat is so close to the coast.
Exactly. The thermal energy off the coast alters the temperature gradients, which steers the jet stream and all the winter moisture it carries directly into California.
But because the Central Pacific El Niño's heat is parked thousands of miles away, out in the middle of the ocean, it excites a completely different wave train.
Yes. It triggers the Pacific North American pattern, the PNA.
And the PNA is characterized by an anomalous high-pressure ridge off the west coast of North America. It essentially builds an invisible atmospheric mountain range right off the coast of California.
That high-pressure ridge acts as an impenetrable blockade. It forces the jet stream to divert far to the north, pushing storms all the way up into Canada or causing them to shear apart before they ever make landfall.
Leaving California completely dry.
The result is a warmer, severely dry California. It completely upends the public expectation. The thermal energy of the 2015 CP event was immense, but its geographic position created a massive drought instead of a flood.
Which brings us back to the diagnostic nightmare of April 2026.
Right.
The NOAA data is showing increasing subsurface temperature anomalies, which signals the deep Eastern Pacific dynamics.
Yes.
But the data also shows significant westerly wind bursts over the Western Pacific, which strongly influence the Central Pacific atmospherically driven dynamics.
We are looking at highly complex mixed dynamics, and that is exactly why forecasting the localized impacts is currently pushing human meteorology to its absolute limits.
It's just too much data.
A longitudinal shift of just a few hundred miles in where that massive pool of heat ultimately decides to park will dictate whether the agricultural valleys of California are submerged under historic floods or decimated by a prolonged crop-killing drought. The atmospheric geometry is that sensitive.
If the variables are that sensitive, if a localized wind anomaly in the North Pacific can trigger a meridional mode that alters the equatorial heat placement, which then alters the planetary wave train, which then determines whether a city floods or burns in CAS. Human analysts simply cannot calculate that chaotic math fast enough.
No, we cannot.
This is exactly why the scientific community is turning to artificial intelligence.
It is a necessary evolution in our diagnostic toolkit. Traditional general circulation models, or GCMs, have served us well, but they are incredibly computationally expensive physics engines.
They try to simulate everything.
Right. They try to simulate the fundamental fluid dynamics and thermodynamics of the entire globe. They struggle immensely with the chaotic, fine-scale processes.
So let's dive into the R-SIFT paper from our stack. It's titled El Niño Prediction based on weather forecast and geographical time series data.
Okay.
This research team isn't trying to build a better physics engine. They're deploying a dual deep learning framework. They want the AI to recognize the patterns of an El Niño, sidestepping the need to calculate every single thermodynamic equation.
The architecture they have built is a hybrid. They combined a convolutional neural network, a CNN, with a long short-term memory network, an LSTM. It is a highly sophisticated approach to handling both the spatial and temporal chaos of the ocean.
Let's break those down. The CNN handles the spatial data. Now, in traditional computer science, we use convolutional neural networks for image recognition, right?
Yes.
Like the AI learns the spatial geometry of a face on your phone or a stop sign for a self-driving car. But here, the researchers are feeding the CNN massive grid-based heat maps of sea surface temperatures from the Niño 3.4 region. It is looking at the spatial distribution of the thermal anomalies.
It acts as the spatial feature extractor. It identifies how the warm and cold patches are distributed across the geographic grid.
Right.
But a single heat map is just a snapshot in time. To predict an El Niño, you need to understand the momentum of the ocean. You need to know how those anomalies are evolving over months and seasons.
And that is where the second part comes in.
Exactly.
Like
That is where the long short-term memory network comes in.
the LSTM. It's a specialized recurrent neural network designed specifically for sequence data.
Right.
The researchers feed it normalized numerical matrices of the sea surface temperature and the ocean heat content. That's the subsurface data we were talking about earlier.
Correct. The LSTM tracks the temporal dependency. It watches the sequence of the matrices to calculate the velocity and trajectory of the thermal mass.
It's kind of like analyzing a football game.
How so?
The CNN looks at the field to see where all the players are standing right at this exact second. But the LSTM watches the video to see the momentum of where they are running.
That is a brilliant analogy. It fundamentally models the temporal evolution of the ocean's heat.
Yeah.
And by merging the CNN's spatial mapping with the LSTM's sequence tracking, the model calculates the future oceanic Niño index, the ONI. And the short to midterm results published in the paper are striking.
How striking.
When blending observed historical data with its own short-term predicted data, the model achieved a 90.57% accuracy rate.
Over 90% accuracy for a coupled ocean-atmosphere system is staggering.
It is incredibly high.
But diving deeper into their methodology, there's a massive vulnerability in this architecture.
Yes, there is.
When the researchers forced the AI to forecast 5 quarters out, so looking 15 months into the future, and restricted it to relying only on its own predicted data without feeding it fresh, real-world observations, the accuracy dropped down to 83%.
That drop is highly significant, and it reveals the fundamental limitation of their current feature set. The AI is suffering from a profound tunnel vision.
Because of what they're feeding it.
Exactly. Its entire predictive universe is limited to temperature and heat content.
Wait, hold on. If the AI's feature set only includes sea surface temperature and ocean heat content, and we just established from the PAIC study that Central Pacific El Niños are heavily reliant on subtropical atmospheric forcing, like the anomalous surface winds of the North Pacific Oscillation, doesn't that mean the AI is completely blind to the very mechanisms that create the CP variation?
That is the exact blind spot. The AI model lacks any input data on surface wind stress.
Wow.
It cannot see the westerly wind bursts. It lacks data on ocean currents, sea level anomalies, and the complex bathymetry of the ocean floor. It is trying to predict the outcome of a highly chaotic, coupled ocean atmosphere system by only looking at the water temperature while completely ignoring the atmosphere pushing that water around.
It's literally trying to predict the trajectory of a billiard ball while refusing to acknowledge the pool cue.
That is exactly what it is doing. And that oversight is why it hits a wall when trying to forecast long term. Even with a dual architecture deep learning framework, the AI falls victim to the exact same hurdle that has plagued human meteorologists for decades.
The spring predictability barrier.
Yes, the spring predictability barrier.
The spring predictability barrier is infamous in climatology.
Mm.
During the Northern Hemisphere spring, which is right now, April and May, the El Niño Southern Oscillation System is typically in its most neutral transitional state.
Right.
The temperature gradients across the Pacific are relatively weak. The signal-to-noise ratio in the data is just terrible. It is incredibly difficult to differentiate the actual emerging trend from the background chaotic noise of the ocean.
It is the equivalent of trying to predict the outcome of a coin flip while the coin is still at the apex of its toss. The physical signals necessary for a highly accurate long-range forecast are simply too faint during the spring. The neural networks, lacking the wind stress data, simply cannot find a strong enough mathematical pattern to maintain that 90% accuracy over a 15-month horizon.
So just to summarize where we are right now, we have a Pacific Ocean that is unequivocally boiling.
Yes.
We have extreme variations in how that heat might manifest atmospherically, capable of triggering either devastating floods or impenetrable high-pressure drought ridges.
Right.
And our most advanced pattern-recognizing artificial intelligence is currently staring at the spring data, fundamentally blind to the atmospheric wind constraints, struggling to tell us exactly where the hammer is going to fall.
Which means we transition from the realm of predictive modeling into the realm of immediate, real-world impact
Thus,
mitigation.
it's already starting.
Exactly, because regardless of whether the AI can perfectly map the trajectory for late 2026, the thermal energy already present in the system is initiating a devastating chain reaction right now. We have to look at how this physical atmospheric disruption collides with the extreme fragility of our global supply chains and human infrastructure.
This brings us to the most urgent part of our source stack. The article from the South China Morning Post outlines the immediate agricultural crisis, and the Nature Climate Change study out of City UHK quantifies the staggering generational toll on human life.
Both are critical to understand.
Looking at the SCMP report first, the geopolitical and agricultural mechanics are colliding in a way that basically guarantees massive food insecurity across Asia.
The SCMP report underscores a critical reality. Climate anomalies do not occur in a vacuum. They apply immense pressure to systems that are already experiencing severe strain. The meteorological forecasts are predicting heavily suppressed rainfall across South and Southeast Asia right as these regions enter their most critical planting seasons. India is forecasting a significantly below-average monsoon season. Australia is projecting a drop to a 7-year low in wheat planting due to persistent, unseasonal dryness.
A suppressed Indian monsoon and a collapsed Australian wheat yield are enough to trigger a severe global commodities crisis all on their own.
Absolutely.
But the SCMP details how this drought is compounding with a catastrophic fertilizer shortage. We have to look closely at the supply chain mechanics here to understand the severity of the threat. The primary foundation of modern global agriculture is urea fertilizer.
Right.
And the primary industrial feedstock required to synthesize urea is natural gas. Now, the SCMP mentions this natural gas shortage is driven by a war in Iran. I want to be very clear to you, the listener. We are not taking any political sides regarding that conflict. We are simply reporting impartially on the information in the source material and how it impacts the supply chain.
Of course. Maintaining strict adherence to the data regarding market availability without delving into the geopolitical complexities of the regional instability in the Middle East. The objective fact is that natural gas exports from major producers, including Qatar, have been severely constrained.
Right.
And this constraint has triggered a massive spike in the cost of raw natural gas.
Which immediately skyrockets the production cost of urea.
Exactly.
So the farmers in Asia are trapped in a lethal vice. The atmospheric high-pressure systems are starving their crops of necessary rainfall, and the disrupted natural gas supply chain has priced them completely out of the nitrogen fertilizers required to keep their soil viable.
It is a worst-case scenario for crop development.
When you combine drought stress with nutrient starvation on a continental scale, agricultural yields don't just dip by a few percentage points. The systemic viability of the crop collapses entirely.
The domino effect is absolute. The agricultural collapse leads directly to acute food shortages, which drives aggressive, systemic food inflation globally.
Everyone feels it.
Yes. The cost of staple grains in Europe and the Americas will surge as the Asian yields evaporate. But the economic impact of the agricultural failure is really only the first wave of the devastation.
Yeah, and this is where it gets incredibly grim.
To understand the true, terrifying scope of a Super El Niño, we have to examine the epidemiological data presented in the Nature Climate Change study.
This study, led by researchers at the City University of Hong Kong and Nanyang Technological University, is arguably the most sobering document in our stack today.
Without a doubt.
It completely dismantles the narrative that an El Niño is merely a transient seasonal weather event that a population simply endures before returning to baseline.
Right, they looked at 6 decades of data.
Exactly. They analyzed 6 decades of comprehensive data across 10 Pacific Rim nations, and their findings are chilling. Extreme El Niños actively and permanently reverse human life expectancy gains.
The methodology of this study is incredibly robust. They didn't just look at direct casualties.
Like from storms.
Right, the tragic, immediate deaths caused by storm surges, flash floods, or landslides. Direct casualties are statistically marginal in the broader demographic picture. The researchers traced the secondary and tertiary mortality surges. They mapped exactly how a shifting atmospheric pressure system physically degrades public health over a prolonged period.
I was analyzing their breakdown of the secondary surges, and the epidemiological pathways are brutal.
They are.
When an Eastern Pacific El Niño triggers unprecedented flooding, Or a Central Pacific event triggers severe drought that forces populations to rely on dwindling stagnant water reserves. The immediate result is the catastrophic failure of municipal water infrastructure.
Right.
This triggers a massive spike in waterborne and vector-borne infectious diseases. You see immediate regional outbreaks of cholera, widespread diarrheal diseases, and an explosion in malaria as mosquito vectors multiply in the stagnant floodwater.
But the infectious disease vector is only one half of the mortality equation.
What's the other half?
The study emphasizes the profound impact of cardiovascular and respiratory stress. The prolonged extreme heat waves associated with the pooling of thermal energy in the Pacific place an immense sustained burden on the human cardiovascular system.
Because people just can't cool down.
Exactly. For populations lacking robust, reliable air conditioning infrastructure, the sheer thermal stress causes massive spikes in heart failure.
And if a Central Pacific El Niño sets up one of those impenetrable high-pressure ridges we discussed earlier, that atmospheric mountain doesn't just block rain.
No, it does much more than that.
It creates a stagnant atmospheric dome that traps industrial pollutants and particulate matter directly over urban centers. The study links this amplified, stagnant air pollution directly to severe spikes in acute respiratory ailments.
The demographic reality is that this mortality is entirely asymmetric. It disproportionately targets the absolute most vulnerable populations.
The young and the old.
Yes. Infants whose immune systems cannot survive the diarrheal diseases, and the elderly whose cardiovascular and respiratory systems simply collapse under the sustained thermal and particulate stress. When a climate anomaly drives a sharp spike in both infant mortality and premature geriatric death, it drastically drags down the statistical average of the entire region's life expectancy.
The historical data the researchers isolated to prove this correlation is just staggering. They looked back at the 1982-1983 extreme event.
Right.
Across the studied regions in the Pacific Rim, the average life expectancy dropped by nearly half a year.
Half a year. Let that sink in.
4 to 5 decades of painstaking medical advancements, sanitation improvements, and public health initiatives statistically wiped out in 18 months by a shift in oceanic temperature.
And the subsequent economic burden is inextricably linked to that health collapse. The study estimated the global economic damage of the 1982-1983 event at roughly $2.6 trillion. When they analyzed the 1997-1998 event, the mortality impact was a loss of roughly a third of a year of life expectancy, but the global economic damage nearly doubled to an estimated $4.7 trillion.
The localized data for Hong Kong alone provides a terrifying perspective on the density of the destruction.
It does.
In 1997-1998, a single weather anomaly cost the city of Hong Kong $58 billion and stripped 0.4 years off their average life expectancy. If the 2026 data we are tracking right now continues to outpace the 1997 metrics, well, I mean, if this 2.5-degree Super El Niño fully materializes, what is the extrapolation? What does the city UHK model predict for the future?
Professor Benjamin Horton, one of the lead authors, outlined a highly concerning trajectory. By extrapolating current population growth scales, urbanization rates, and existing economic metrics, the model suggests that if these extreme El Niño events continue to intensify in frequency and severity, the cumulative economic damage to Hong Kong alone could reach up to $300 billion over the course of the 21st century.
And the global extrapolation.
Across the entirety of the Pacific Rim, the models project up to 2.8 years of life expectancy permanently lost by the end of the century.
2.8 years.
Yes. And they estimate a staggering global economic burden of $35 trillion. The central thesis of the City UHK study is that we must fundamentally reclassify how we view El Niño. It is no longer an episodic natural disaster. It is a chronic, systemic threat to the biological and economic stability of the human species.
Which brings us to the final, most haunting concept presented in our source material. An analysis in the Sunday Guardian discusses the rising probability of a climate regime shift, or CRS.
Right, the CRS.
The CRS is defined in climatology as an abrupt, profound, and persistent transition between alternative stable states in a complex system.
It represents a fundamental breaking of the equilibrium. A standard El Niño bends the climate system, it disrupts the norms, causes seasonal damage, but eventually the system snaps back to its historical baseline.
The bathtub levels out.
Exactly. The fear among climatologists is that a 2.5-degree Super El Niño, occurring within an ocean that has already been systemically warmed by decades of rising baseline temperatures, possesses enough thermal mass to push the entire planetary system past a tipping point.
So the system doesn't snap back. The metaphorical bathtub doesn't level out.
No.
The 2026 anomaly acts as the catalyst for a climate regime shift, establishing a permanent new baseline of elevated planetary temperature, permanently altered agricultural jet streams, and structurally degraded human health.
It is the transition from a transient anomaly to a permanent state of altered atmospheric physics, and it demands a total paradigm shift in how global societies manage risk and infrastructure development.
We've covered an immense amount of incredibly dense ground today. We started by looking at the raw diagnostic data of April 2026, tracking the unprecedented buildup of subsurface heat and the intense westerly wind bursts driving Kelvin waves across the Pacific.
We did.
We examined the critical structural differences between the deep ocean-driven eastern Pacific events that flood the coasts and the atmospherically forced central Pacific events that build high-pressure drought ridges.
We analyzed the architecture of the deep learning AI models attempting to map this chaos, recognizing the brilliance of combining convolutional neural networks and LSTMs while identifying their critical blind spots regarding atmospheric wind stress and the spring predictability barrier.
And we grounded all of that atmospheric physics and predictive modeling in the stark, quantifiable reality of the human toll. The compounding geopolitical supply chain failures, destroying fertilizer access, the collapse of Asian crop yields, the $35 trillion economic projections, and the brutal epidemiological pathways that are physically stripping years off human life expectancy through disease and cardiovascular collapse.
If there is a unifying takeaway from synthesizing this extensive array of source material, it is that we possess unprecedented, highly granular knowledge. We understand the thermodynamic mechanisms. We understand the structural flavors of the anomalies. We have empirical data proving the precise vectors of mortality and economic ruin.
We know what's happening.
Yes. The uncertainty no longer lies in what these events are capable of doing. The uncertainty lies entirely in how global societies will choose to utilize this data to adapt.
Which leaves you, the listener, with a very specific, localized challenge. We spent the last hour discussing global GDP projections, oceanic thermal dynamics, and deep learning neural network architectures. But the impact of a climate regime shift will be hyperlocal. It will happen on your street.
Absolutely.
I want you to critically evaluate your own local community's infrastructure. If a historically unprecedented weather anomaly locked in over your region tomorrow, whether it is an unrelenting month-long deluge driven by an eastern Pacific wave train or a brutal stagnant heat wave and drought driven by a central Pacific high-pressure ridge, is your community prepared?
It's the most important question.
Examine your municipal water treatment facilities. Are they built to withstand catastrophic flooding without cross-contaminating the drinking supply? Look at your local hospital systems. Do they have the surge capacity, the specialized equipment, and the localized power generation to handle a massive, sustained spike in respiratory and cardiovascular failure? Assess your regional energy grid. Can it handle the peak load demands of a prolonged, extreme thermal event without cascading blackouts?
We have to look at our immediate surroundings.
Are the systems that keep you alive designed for the mild, predictable climate of the late 20th century, or are they actively being hardened to survive the climate regime shift of 2026? It is no longer a theoretical exercise for academic climatologists. The Pacific Ocean has delivered its diagnostics. The thermal mass is already in motion. The only variable left is our resilience. Thank you for joining us on this deep dive into the source material. Stay curious, stay informed, and start asking the hard questions in your own backyard. We will see you next time.